Two major advances have just happened in quantum computing. First of all, IBM is working on a very exciting project. They are building a quantum-centric supercomputer. The idea is to build on the way classical supercomputers work, but combine quantum processors together with classical CPUs and GPUs into a single computing system. They're going to build the most powerful supercomputer by taking advantage of quantum mechanics and quantum communications. And this will completely transform the way we do large-scale computing. This new quantum-centric supercomputer will be based on Quantum System 2, with multiple quantum processors connected together. To be specific, they will be using Heron processors. It's 133-qubit processors. Many of such quantum systems will be connected together, and the whole idea is to build a modular system, just like we have it in a classical data centers, so we can connect as many systems together as we want. And in this way, scale quantum computer. Here is the illustration of the future quantum-centric supercomputer. You see, it's built of 4 such quantum 2 systems. Each system combines many quantum processors, control units, and cooling for the qubits. And all these 4 systems interconnected together in classical and quantum ways. And all of this amazing engineering results in a 100,000 qubit supercomputer. At the moment, the largest IBM's quantum processor is Osprey with 433 qubits. Meanwhile, D-Wave released a prototype featuring more than 500 qubits, and their largest quantum system at the moment features 5,000 qubits. But we actually need more. It is estimated that we need at least 100,000 physical qubits to build a practical supercomputer, which will be set to tackle the most challenging problems. To get to this point, there is still a lot of work, a lot of innovations to be done, in particular to integrate classical and quantum workflows. Here, we need innovations at all the levels of a computing stack. So starting from the hardware, interconnect, firmware, and also software. On that, IBM team is collaborating with 2 universities, the University of Tokyo and the University of Chicago. They both have very advanced research in the field of quantum computing. They will be building this quantum-centric supercomputer together, and it's planned to be ready by 2033. So in 10 years. Wow. Let me know what you think about this idea of mixing classical and quantum ways of computing. Leave me a comment below. I see here a lot of potential for kind of unlimited computing power. Now to the second breakthrough, which is actually coming from a small startup called CQC. These guys have made just a major leap forward by removing a lot of wires. Let me explain. One of the major bottlenecks of scaling quantum computers to larger number of qubits are wires. A lot of wires. At the moment, IBM and Google using a lot of wires to control superconducting qubits. These wires are required to manipulate and measure quantum bits inside quantum computer. This means each bit gets wires, which directly connect the electronics at room temperature to the qubits at the cryogenic, so millikelvin temperature. Even if we are talking about small 50-qubit quantum processor, it's already getting crowded. The problem of this approach is that the more qubits we have, the more wires we need. And with adding every qubit, we add more and more wires to the system. And this scales poorly. Moreover, all these wires and components generate heat that disrupts qubits. Ultimately, the goal is to minimize the number of wires which go into the fridge. And this problem must be addressed to ensure the scaling to larger number of qubits. The solution is to bring as much readout and control electronic as possible to the fridge, or even, if possible, integrate it onto the qubit chip itself. And this is exactly what the startup CQC did. They've developed a microchip for controlling qubits, which operates at cryogenic temperature. This means they can bond this microchip directly with a quantum processor. And this is brilliant. Using this chip, they encode data in the form of magnetic fluctuations. In this way, this chip eliminates all the extra wiring and also reduces the complexity. And with this approach, they reduced the number of generated heat, which was disturbing the qubit performance. What's interesting, at the moment, IBM is solving exactly the same problem, but they're doing it in a different way. They're doing it with cryogenic electronics, with so-called cryo-CMOS, which is able to operate at cryogenic temperatures. However, these cryo transistors generate much more heat, and that's the problem, because they can't integrate it together with a quantum processor. But the new chip from CQC can be integrated, and that's amazing, because this is another leap forward towards building a practical quantum computer. If you want to understand how quantum computers work, Brilliant offers a variety of courses on quantum computing. They will teach you everything from the basics: what are quantum bits, what is entanglement, how quantum circuits and quantum algorithms work. After each lesson, you'll be solving practical problems and quizzes, which is the most effective way to learn. What I like about Brilliant is that they really embrace this concept of learning by doing. Like this course, you can write your Q-sharp code and run it on a quantum computer, and this is fun. Apart of courses on quantum computing, they also offer courses on artificial intelligence and computer science, which you can take. And they actually extend the collection of their courses every single month. If you want to try Brilliant, use my link brilliant.org/AnastasiaInCzech and sign up for free. With that, you can try all the courses on Brilliant for 30 days for free. And the first 200 subscribers who will use this link will get 20% off annual subscription. Thank you for watching, and I will see you in the next video. Ciao!